Hi everyone, so in this video we're going to tackle another sort of problem which is also related to algebraic equations. This one involves actually an exponential function as we see here. So the problem that we are solving in this video is the solution of this problem. So x exponential of minus x is equal to a small number. Well, as a matter of fact, this is a transcendental equation, right? It does not accept any closed form solution. And a numerical technique is certainly the only way to get a solution to that equation, all right? But numerical techniques can sometimes, they can be helped by some semi-analytical formulations like perturbation techniques, in which case they can provide, the perturbation methods can provide a first very good guess of the solution that can then be fine-tuned by means of appropriate numerical techniques. All right, so that's typically the spirit in which we are going to tackle this problem. And just to get a better picture of what we need to do here, I have represented here, I've just plotted the exponential x times the exponential of minus x, which is this function here, highlighted. And what we need to do is to find somehow the intersection with a certain level epsilon here, which is supposed to be very small, all right? And so quite immediately we can notice that there are two roots. There's a small root and there's a kind of large. Let's call it large, and let's call this one small, all right? So we're going to focus on these two roots. We can also notice that in the unperturbed problem, that's something I always try to force you to start with, unperturbed. Problem would say x exponential minus x is equal to 0. So in fact, we have two options. Either x is equal to 0 or the exponential is equal to 0, but this actually doesn't work too much, but we see that the second root actually is coming from plus infinity. So we have a root here. We can qualify this as a regular root, and the other one is going to be a singular root. All right, so we do expect now, based on what we've seen in the sequence of videos B, that a regular root can be obtained quite easily. Let's just see together how we can solve this. So first, let's start with a small root. We could start with a regular expansion in the form x0 epsilon x1 epsilon square x2. Okay, check if this works. If this is fine, then we are all right, and then we can proceed further. And if not, we'll try to find something else. All right. So if we just substitute this ansatz into the governing equation, what we have is x0 plus epsilon x1 epsilon square x2 multiplied by the exponential of minus x, which is of course, yeah, x0 plus epsilon x1 epsilon square x2. What do we notice here? That x0 is in fact equal to 0, right? Because if you want to balance the different orders of magnitude in this problem, then you realize that the only possibility is to have x0 is equal to 0, which is at the same time the solution of the unperturbed problem, right? So I was probably a little bit fast when I started with this sequence over here, because what we just observed is x0 should actually be equal to 0. All right, so there's of course a dirty way to do, all right, because if x0 is equal to 0, what you could do is just discard these terms, then simplify out left and right by epsilon here, you see. So what we would end up with is x1 plus epsilon x2, and then we need to get something that we can use, but you see that here, because we're looking for a root which is in the neighborhood of the origin, I mean in the neighborhood of x0 is equal to 0, the argument of the exponential is something that is quite small. And if this is something that is quite small, then we can expand this in the neighborhood of the origin, right? So I'm just going to use a series expansion. So maybe you want to remember that the exponential of minus y, when y is a small number, is 1 minus y plus y squared over 2 minus etc. etc. When y is in the neighborhood of the origin. So let me just write something like this. So we have here 1 minus epsilon x1, and then certainly there will be terms of order epsilon squared that I don't want to keep, so that the equation becomes x1 plus epsilon x2 squared. I'm sorry for this. And then we have minus epsilon x1 squared plus terms of order epsilon squared, and this is equal to 1. All right, so at leading order, we have x1 is equal to 1. Then at the following order, we have x2 is equal to x1 squared, which is equal to 1, and then we could keep going this way. And we end up with the solution x is equal to epsilon x1 plus epsilon squared x2 plus higher order terms. All right. And so I said this is probably a dirty way to proceed, because if you notice right away, what is annoying here just a little bit, it's not dramatic of course, but what is annoying here is that the leading order is of order epsilon left and right. So we had to divide, going from here to there, we had to divide by epsilon. This is something that could have been avoided for sure if from the beginning you notice that the order of magnitude of x should be epsilon, right? So if you just observe that we want to solve x exponential of minus x is equal to epsilon, when x is a small number in the neighborhood of the origin, the exponential of something small is almost equal to 1. So this has order of magnitude 1. And so what we're looking for is an x which is of order epsilon. All right. This being said, if x is of order epsilon, then what we're supposed to do is to use or introduce a rescaled coordinate, substitute this in the governing equation and see what it gives. All right, but then the problem would become x tilde times epsilon multiplied by the exponential of minus x tilde epsilon is equal to epsilon. And now we can clearly and neatly divide by epsilon, so that the problem we start with, and this is really the beginning of the story, the problem we start with is something that is of order 1. All right, I just don't want to be picky about that, but it's just that in order to be clear, make sure you start with something that has orders of magnitude 1 left and right. I know this is probably not a big difference in such a simple problem, but as you will tackle more complicated problems, it's very important that you, as the guy who is just deriving equations, it's very important that you keep track of the different orders of magnitude you have everywhere. All right. And of course, I'm not pushing this further, but if you keep going this way, just substitute this regular ansatz in this new equation, and of course we'll end up with exactly the same solution. All right, this can be left as an exercise if you have just 2 or 3 minutes to spend on that. So let's focus now on the large root, which is probably something more interesting here for us. And concerning the large root is something that is going to be a little bit more difficult, right? Because definitely the use of a regular ansatz or a regular sequence like this is something that will not bring us to the right solution. Okay, and why is that? Because simply, if you want to substitute this regular ansatz into that equation, you will just realize that x being large, you need to find some sort of approximate solution of the exponential, approximate expression for the exponential of minus x when x is something very large. So we're coming close to 0, so this is a small number, but this small number actually is not epsilon, is not of order epsilon. And so we actually here, we struggle in, definitely we struggle in finding the right sequence. Finding the right sequence. And what we've seen in previous algebraic equations is that usually the sequence was a sequence of this kind, all right? Or a sequence with non-integer powers. Sometimes that also happens, right? And we even did something a little bit more complicated in some of the videos where we have the fourth root and we have also epsilon 2 powers with the fractional numbers, right? But you'll see here that the sequence we need is even more nasty, especially when you meet this kind of problem for the first time. And basically the only approach that is available here in order to get a sequence is the iterative method. All right, so if we just remember in the iterative approach, which is something I just also briefly introduced in the first B videos, in the iterative method, you rewrite the governing equation in such a way to keep on the left the dominant terms and on the right the remaining terms, all right? So remember here, we need to keep on the left dominant terms and others on the right, others on the right. Well, in this case, this is quite straightforward, because we just have two terms in the problem, right? We have one term on the left and one term on the right. Which one governs in this tail here, which decreases very fast? Well, definitely what governs is the decreasing nature of the exponential, right? So the dominant term is definitely something related to the exponential. And in the iterative approach, in the iterative method, what do? We need to keep on the right things that do not depend on the dominant term. So I could keep x on the left here, but you see there's no way to obtain an iterative approach if I do that. All right, so what I have to write is something that looks like this. So I keep the dominant term on the left. This is dominant. And on the right, there's no other option. I have to bring the x on the right in order to create an iterative method. And this is it. All right, so the following question is how to initialize this series. Initialize this series by giving an appropriate value for x0. All right, maybe we could, before doing this, we could just try to get an explicit expression for xi plus 1. So if you just consider the inverse of this, left and right, that's what you have, meaning that xi plus 1 is equal to the log of x1 over epsilon. And this is how we're going to iterate, all right? We're going to iterate with this relation. And so coming back to x0, you see that what we need to do when you want to start an iterative method, we would like somehow to converge to that point, starting from somewhere. you don't necessarily have to start from far, because you don't know how far you need to start, right? You know that this root, when epsilon goes down to 0, this root is going to go to plus infinity, all right? And so if you want to start from the right of the root, you need to be, well, further away than infinity, right? And nobody has ever been there, except maybe Chuck Norris once or twice. So the best option is definitely to start from the bulk, all right? So this is the bulk of the domain in this area. It means the body or the central part. So start from somewhere over there, and if the problem is well settled, if the iteration method that you settled is right, then quite quickly it's going to converge to the root you're interested in. And so basically you see that you can start almost anywhere in the bulk, maybe not too much on the left, right? We could try with xi, try x0 is equal to epsilon, all right? So what would it give? It would give x1 is equal to the log of epsilon over epsilon, log of 1. This is 0. This is bad, right? Because we're going to the left. It goes to left. All right, so we started at x is equal to epsilon, and after one iteration, we ending up at x1 is equal to 0. So that's bad. So let's try a little bit more to the right, and a little bit more to the right could be, well, something over the 1, right? So there's nothing bad starting with x0 is equal to 1. I'm just choosing the next order of magnitude. And this would provide x1 is equal to the log of 1 over epsilon. And this is indeed something large, right? Because if epsilon is small, 1 over epsilon is large, and log of large is large. All right, so it's good because it means we are going to the right, All right. And so probably, in fact, this is probably just the order of magnitude that we should expect for the roots, although I don't feel so much confident talking about orders of magnitude when the sequence is not a sequence in integer powers of epsilon, right? We understand here what we mean by orders of magnitude. But in this case, this is probably just the first term of a sequence. And one way to observe this is actually the first term of a sequence is just to keep going, right? If we compute x2, which would be a better approach or a better estimation of the root, we would have the log of x1 over epsilon. And this is the log of 1 over epsilon multiplied by x1. Okay, let's just remove this. So the log of 1 over epsilon times the log of 1 over epsilon, like this, which in fact means we have the log of 1 over epsilon plus the log of 1 over epsilon. Okay, wow, you see that's quite complicated. And if we keep going, we would definitely, I'm sure we would get it quite easily, all right? For x3, this is the log of 1 over epsilon plus the log. Let me just write it like this to make sure this is a little bit shorter. But we definitely understand that the log only applies to 1 over epsilon. All right, and so you see that in fact we have here in this case we have a sum of terms that are smaller and smaller, and because of that we see that we have nothing but the sequence that we were looking for. All right, so you can consider this. Can consider this as the different terms that you should use in the asymptotic sequence. All right, and so it's just as if we had x0 is equal to 1, x1 is equal to 1, x2 is equal to 1, and so forth. And the different power or the different terms we use in the sequence are not any longer powers of epsilon, but they take a different shape. All right, and well, that's basically it. That's everything I should say about this problem. But now we can also try to check how this can be useful to just inform a numerical method that could be used in order to solve the problem, right? And so, for instance, if you want to use now a numerical technique in order to solve the problem, so I don't know, Newton-Raphson approach, for instance, which is one way to solve differential equations, transcendental equations in a numerical manner, you could start from one of these approximations of the roots and, well, just use any of them, and that would work. And sometimes, in this case, this is something that is feasible. It is also possible to bracket the exact solution, all right? And so I'm just going to illustrate this. It is possible to bracket the solution. And so the way this is performed, it's probably something that you can do on a case-by-case basis, right? There's nothing really general about that, but if you just do some trial and error, that's something you can achieve. And so what I mean here is that if we're looking at x1, I would just first like to convince myself that it is on the left of the exact root. All right, so this is the exact root. Let me just call it x star, all right, because this is the exact solution. X, and I just plot both x exponential of minus x and epsilon over here. All right, and so just to observe that x1 is on the left, let's just compute x1 exponential of minus x1. And if this is if this is larger than epsilon, it means that x1 is on the left. If this is smaller than epsilon, it means that x1 is on the right. All right. And so if we want to compute this, then let's just substitute x1 in that expression. And x1 is what we have underlined over here. This is the log of 1 over epsilon. So we have the log of 1 over epsilon multiplied by the exponential, or divided by, let me just write it this way, I could divide by the exponential of x1 and the exponential of the log, so I need to divide by epsilon, right? So this is times 1 over epsilon. So it means we have epsilon times the log of 1 over epsilon. All right. So, and we would like to know whether this quantity is larger or smaller than epsilon. All right, that's what we want to do. That's what we want to assess. Well, this is quite easy because we see that we have epsilon and epsilon over there. So we need to determine whether the log of 1 over epsilon is larger or smaller than 1. And definitely the log of 1 over epsilon is larger than 1, meaning that indeed we are on the left. All right. So this means that x1 is smaller than x star. All right. Let's try with something else now, and because we can try now to find another point which could be on the right. And just as a test, I said this is something that works usually as a trial and error. I'm just going to try with 2x1, all right? And so let's just replace 2x1 in the expression of x exponential of minus x. So we have 2x1 exponential of minus 2x1, or 2x1 divided by exponential of 2x1, or 2x1 divided by exponential of x1 squared. Or again, 2x1, let me just now replace by x1. We have twice the log of 1 over epsilon. This is 2x1. And I need to divide this by exponential of x1. This is 1 over epsilon squared. So I just multiply by epsilon squared over there. All right, and what we need to do now is to assess whether this is larger or smaller compared to epsilon. All right, so this comes down to check whether twice epsilon times the log of 1 over epsilon is larger or smaller than 1. All right, and what do we have here? We have something that is large multiplied by something that is small. But you might remember that in the limit cases, the integer powers, or the powers of the function that you are interested, actually grow and lead over the logarithms. All right, so it means that when epsilon is going to 0, this actually is going to 0 as well. If this is hard to understand, just replace epsilon by 10 to the minus 3, and you'll see that this is much smaller than 1. All right, and so this means that twice x1 is larger than x star. And so if you combine these two conditions that we found, we get that x star, the exact root, belongs to the interval x1 to x1. All right, and based on that, and that's even better, because if, for instance, you'd like to implement a method like the bisection method, which is another numerical method to solve that kind of problem, then that's something you can do, because you have at your disposal, you have a bracket, an interval in which certainly the root is. All right, so bisection is a little bit slower than Newton-Raphson, but still is something convenient to implement. All right, so we could just, to finalize, just have a look at the exact solution to the problem here. And so what we have represented here is, you see here, I'm just going with you through the different notations that I use in Mathematica. So this is the exact solution. I just compute x as the root of x exponential minus x minus epsilon. So this is equal to 0. And I just define this as a new function, all right? And I can then plot the exact solution as a list plot. So I'm going to build a table mapping the values of epsilon and the exact root for different values of epsilon, ranging from 10 to the minus 3 to 0.05. And these solutions are represented as dots. These are the blue dots you have in this plot. All right, so that's the exact solution. And then on top of that, I'm going to show several plots on each other. I'm going to superimpose not only the exact plot that I've just discussed, but on top of this, I'm just going to also overlay the log of 1 over epsilon, which is the first approximation here. That was x1. On top of this, I plot the log of 1 over epsilon times the log of 1 over epsilon. That was x2. And you see here we have x3. And so using only 3 iterations, you see that the quality of the approximation you have is something that is already very, very good. All right, so when the iteration method is combined or is used to solve problems involving exponentials, typically you don't need so many terms in order to converge very quickly to the roots. Okay, and so finally, what we have here is a comparison between x1, all right, which is the log of 1 over epsilon, to x1, which is now in orange over here, and the average between these two quantities. All right, so here we have 1.5 times x1. Just to say, it's another way to say if you want to solve the problem with a numerical method, then just start at the midpoint of the interval we stated. So just between 1 and twice, x1 and twice x1. And you can start from there in order to get better estimates. And you see that we actually start quite close to the exact solution when we start there. This is probably just specific to this problem. There's no way you could just guarantee that if you do this, you get better and better as epsilon grows in this case. But you see this is not asymptotic, definitely, because when epsilon is getting smaller, we have a worse approximation, all right? We just worked with the average of two bounds that we provided for the interval, so there's no reason that we could get very interesting properties for that. All right, so I hope this was clear. Just to wrap up very quickly, what we've seen in this problem is a small solution that could be tackled with a regular expansion, so nothing really fancy. Just keep in mind that if you have a nonlinear equation like the exponential of minus something small, you're of course always free to use an expansion in the neighborhood of the unperturbed solution, which is exponential of 0 in this case, which provided 1. And then for the large, keep in mind that for the iterative method, you need to use the dominant terms on the left, and then based on that, you provide an iterative method in order to determine successive iterates, which provide better and better approximations to the solution. Then to initialize the process, start in the bulk, which is much better than to start behind the root. And to know where to start in the bulk, well, just start something small and then increase the order of magnitude. If this was not successful, just keep going to the right as soon as you observe that x1 is in fact much larger than x2 if you're expecting roots going to infinity. All right, so hope you enjoyed and keep going.